ничего.
Так.
Хорошо, and now I am going to the second part of the lecture. Actually, in the lower rank, I also discussed this question. We now have to tell what will be the canonical word for cyclic words. So if we have a cyclic word, also we have to know what will be its canonical form. So actually this is simple. We just look a big power of this cyclic word, and then we take its canonical form. And then it turns out that actually, aside from some boundary disturbance, the rest will be a periodic word itself, and not depending if we have a big power of this word, inside this it will be periodic also. Maybe outside 3 periods from one side, from 3 periods from other side, but the rest will be periodic. This is just when we go through all these definitions of the word, and we see that the result will also be periodic. I mean,
why 3 periods?
Maybe,
why not 2?
Maybe 2, but just to be sure. So the sure side is 3, even 2.
Okay.
Because then we look what will be the one, what will be the one layer map. Then when we are able to look what will be the certified map, also we need to take out 1 or 2 periods on each side. It doesn't matter, we can take an arbitrary big power, so it doesn't matter. And then we take the local decision for the one layer map, and it will be periodic because in a period we have the same kind of the situation. Then we and then when we identify the flats, they will be identified in the same way in each period, whether they're flat, and also when they're composite, also the situation will be the same when we move it by period. So apart from some number of periods on the ends, after all we will have the same decision in each place, so the result will be periodic. So we can return and take the cyclic word of this, which will be defined to be the canonical word for the cyclic word. By the way, it should be also the same for each relator, because the angular relator, as we look at it, is a cyclic word. So we will, in this way, define the canonical form for the angular relators. But we actually need much more, because we need to know the combinatorial structure of the canonical form. So for angular relators, we have to establish the combinatorics of the canonical form. So, what we use for this, let me recall. In any case, the angular relator is a covering of the flexor. If we take B on one side and B on the other side, then we just, the whole angular word, it's is some power A, then B to the power epsilon 1, maybe positive or negative, then A is in this direction, B to the power epsilon 2, etc. This will be the form of the angular relations when this exponent depends on the particular way of form of the angular relation. So all this is a covering of the pretzel because we give it this way, then positive or negative here, backwards A, positive or negative B, etc., etc. So the angular relator is a covering of the pretzel.
Pretzel is this one, yeah?
Now, in four exceptions, because when we take this angle board, then we have b to the power alpha and b to the power alpha on one side, b to the power beta and b to the power beta here, and this one we call it T2 depending on A and B. And T2 is of course of this form that we discussed here, but also in some exception situation we have the second power of B when we take a horizontal and vertical forms of this cell and take them together. So in B we have B2. So actually everywhere that is plus minus 1, in four places we have some positive or negative, maybe big power of B, and in one particular place we have B squared. So then, as we told, we can assume that A is much bigger than B. Then we can just compute it, because it may happen, for example, that B is much shorter than B, will be much shorter than A. For example, we have B, A, then B, maybe very short, for example, and we have A on the other side. And also we can assume our A already could be assumed basically symmetric on both sides, because when we take it from the previous relation, so it itself is symmetric. So we have some B in the middle of A, which we now, and so it goes the same in the same way. So we have to compute this. A itself could be assumed canonical, B itself could be assumed canonical, and this is symmetric. Then we have to compute two canonical triangles with B, because this long A may be short B, and then this is to take what happens on the in between, and also to take the other part, the canonical triangle. In any case, we will have here, it's so, why I'm saying it, because maybe B is very short, maybe nobody can tell, maybe they take a single letter. A is long, because it is a particular section RK, but B may be short. It may be a little less shorter than A, or maybe very short. All the possibilities are open here. In any case, when we take this word, we are able to compute its canonical form. And then we actually means here we have two possibilities, whether we go, we may cross this in a positive way, or we may cross in the negative way against this. And then we have the same thing will happen on the other side, because A itself will be symmetric. In any case, we have a very particular structure of this. And then, when we take the covering of it, this will give us the combinatorial structure of the canonical form of the angular relation in rank K. Except for these places when we just take a definitely big power of alpha, and then it will depend on this power in the way how we calculated this was indefinitely big power of B in both relations. So we just will, and we will have also some canonical triangle on the end of this, and the rest will be just depending on the power of B as a parameter. But with few exceptions. It could be two exceptions for small values of b. Power 2 will be another exception, and some other 3, 4, etc. for small exceptions, but this will be until we calculate this. So actually we have a finite number of possibilities of the combinatorial structure of the canonical form of the angular relation. All the rest will be just a covering of this what the computer did, and here we have some particular cases which we have to take into account. In any case, this will be the canonical form of angular relation. And then in rank K, and then we assume that all the relations in rank K plus 1, K plus 2, etc., they all are already in this canonical form. Okay, so then the following happens. We now take the Ranke Van Kampen diagram, in which all ranges of all possible ranks could be present simultaneously. And then what we do, we now start to define the series of derived maps. This is done exactly in the way it is in the Israel Journal paper. It means that when we have this rounded one something diagram, so I mean each region has itself its own rank, etc., etc. So we define the series of derived Van Kampen diagrams. What will mean the first Van Kampen diagram? We take all the regions of rank 1 and we divide them between the regions of higher ranks. We assume that the regions of rank 2 has the biggest attractive power, then the regions of rank 3, etc. It goes up to the distance, because then for each region we look what is in distance to the regions of higher ranks. How do we define the distance? If it has a common edge that will be on distance 1, the next one having a common edge will be of distance 2, etc. So for each region of rank 1, we look what are its distances to the regions of rank bigger than 2 and bigger. And then this is attaching to the region which is the smallest distance to it. And if there is the same distance, then we look what is their attractive power. These regions with rank 2 will be given a preference, and between themselves they ordered in some way that with the stronger one will take it if there is a conflict, and etc., etc. So now after this, we will have the first derived map. Now, in order to be able to continue with this procedure and to derive information from this map, we have to establish the properties of this map in each stage. So the first one that we needed, and in case initial is very easy to achieve, if we take a map, a region of rank 1, and if it is an inner region, so all of this, if all its neighbors are also of rank 1, then their number is very big. Because particularly we computed for our parameters, the common part is 2 to the power negative 26 of the common part. So actually it will be many neighbor regions if it is an inner region and all the regions are of the right rank 1.
If it is angular relations, over different words, but then it is common puzzle the same until later we have less.
No, if not, right, if it is the same, that we glue them
Yeah.
together.
Okay.
And then we only look on this composite. So our regions of rank 1 are actually this, or each rank are these composite relatives. Because, of course, and then we can decide on certain constant when we do the gluing and when they abstain. And of course, we can take a very small part of it when we do not continue the gluing. In any case, the common part of this composite relation, in any case, will be small. It means that any inner region, if it is surrounded only by regions of rank 1, it will many of them. Actually, for the structure to follow, we need to take 9. It's a very easy thing to achieve. But we also need another condition, that if this region is one of some higher rank, and the rest are of rank 1, then we need this at least 5 of rank 1 and 1 it is on the boundary of the higher rank. Now, actually, immediately this is also easy to do, because, why? Because this region, this is actually canonical in rank K. When it is canonical in rank K, so it is semi-canonical for certain constant. So it could not be much bigger than a half of the region 1. Otherwise, it would not be semi-canonical in rank 1. It should be semi-canonical in rank 1 and also canonical. If it is canonical in rank 1, it's also semi-canonical. So it could not have much bigger than a half. Actually, if lambda 0 doesn't matter, lambda 0 on part 1, then the rest, if all of them are of region of type 1, then all of them have many of them, because here the contact between regions of rank 1 is very small. So of course we have more than 5 of them. Okay. So this is needed to be able to discuss this first derived map. But then, when we have this first derived map, if the first was regions from 1 to R, the next will be from 2 to R, because now we eliminated all the regions of rank 1. Instead, we have bigger composite regions from rank 2 to R that attracted to them all the regions of rank 1 and distributed between them. Now we have to check that the similar condition holds for this derived map, but then now we take in the derived map things of rank 2, because this is the smallest rank in the derived map, and then we have something here bigger or equal than 3 and of rank 2. And then we need that in this derived map, the same condition must be satisfied. And so we will see why it should be satisfied. If we are able to prove it, then we move to the second derived map. Then we also take all these regions of rank 2 that are in the derived map of rank 1 and distribute them between regions from rank 3 to R in this way we arrive at the second derived map. In any case, we need an estimate why with the will corresponding we have many neighbors. So assume we are able to do this until we reach the rank K, and now we are going to look what will happen in the K plus, this was in the first wave 2. In the case, so we are looking now on the derived map of the K derived map. This K derived map will have regions from K plus 1 to R, because all the, in the first derived map we have a 2 and r, etc. For the derived map number k, we will have derived maps from k plus 1, etc. So by induction, so we assume that all these previous steps could be done. So we're looking now in what happened in this next derived map. So actually we have two possibilities. If both of them are of the index of rank k plus 1, and then we k plus 1, this is one possibility, and then we needed actually if there are at least 9 of them, and the other possibility is that one of them is of rank k plus 1, and the next will be of some rank s that is bigger than k plus 1. So, because we have our previous assumptions are all, then all these maps have the so-called convex layer structure. It means that we look on the derived map of k. So all of them are here in kind of layers, which here also of layer k, because when we did our case step, so we actually take all the composite regions of rank k and attract it here to the rank k plus 1, and here to the rank s maybe bigger the k plus 1, or both of them are of rank k plus 1. And then we use something that's already standard in this situation. How do we measure it? By taking the transversals. Transversals are defined by induction. So first we have the transversal inside this layer structure of rank k. Now then, actually we have to do, this is the inner original k plus 1, we have to take the transversals to the original one, and we measure here. And the same we do on the second side. So we have the transversal here, and then we have to take it to the inner original region of rank s. This is by induction. Now, and the same if there was a situation here. So then we have the following alternative. Either if they are not close to the actual boundary between them, then we know that this projection is small, actually no more than 4 regions of the type K here, and 4 regions of the type on the other side. This is a lemma for this one, for these maps with complex layer structure with 2 types. So then we have here 4 of the type K, 4 of type K, and then we assume by induction that when we go to the original, the transversal still have a small measure, and therefore it must have many neighbors if all of them of the same kind, of here a half of, little more than a half of this, and also many of them. You know, it's small, this is just small entities. Now, so the main case to consider is then we have, possibly have here, in this case, this is a stronger attraction here. Maybe a long series of regions of type K. And this was K, and this was K plus 1, excuse me, and this was bigger than S bigger than K plus 1. This is one situation, and the other situation was then this is k plus 1, this is also k plus 1, and here is a long series of regions of rank k, I mean this, so they were attracted on the step of the k derived region in this and this in the other one. So we have a long series of sub-regions. This is the main situation to have to discuss, and here is the thing. Now, basically, what we do, we look on the original region inside this. By induction,
So, recall
Yes.
my main goal. So my goal is
to show that a region must have many neighbors in the box. So, how do? We just compute this taking the transversals.
How it's related to the canonical forms.
Or, yes, we'll see. So, what is our objective? We know that inside it is the original region,
Yes.
and also here.
Yes.
And the transfer, how we measure the distance, we take the transversals of both sides. And then we actually have to say that this could not be big, because if it is small, it must have many neighbors.
Okay.
The same this situation. This is symmetric, this is symmetric, bigger and smaller. In any case, we have the same question. So, first, by induction, we consider, for example, this map and this map. And then we assume by induction, now actually what will be? And that will be the next one, because it have roughly half on both sides, and their common part is very small. So then we claim that we will have in some place a meeting between the original k plus 1 and the original k inside this. This is claimed by induction. Because then between them we have a region of regions k minus 1, and the same argument when we show that they will have a direct meeting, then they actually by induction have a direct meeting here. And with the rest of this, but I don't claim that all of this is the boundary. There's some place where they meet, not more than this. So they have, so what happens? They have a direct meeting between them. Actually, the situation is a little more complicated in the following sense, that maybe here is some place, and applying the Arrhenius theorem, we can make a surgery that after this original will have a direct meeting with the original of this. But you cannot claim this simultaneously. In any case, what we do? We have here, this one is a part of the original region, so it is canonical in rank K. Because the angle relation is, as we define it, canonical if it is of rank K plus 1, it is canonical in rank K. Because when we take the angle relations in the next rank, we assume they are canonical in all previous ranks. And the same we can claim here, so there also can be a direct meeting, but when we move this inner to another side. In any case, so what we do now? Now we are going to compute the canonical form for this part on one hand, and to compute the canonical on the other hand. Now, and then we claim that when we apply this process of taking the canonical form, that the outcome should be symmetric. Why? So what we do? So let us fix this point. And now how we compute the canonical form? One, we define it is already a canonical, we know. So we know the outcome. This will be the outcome of the computing. Because this is already canonical. So what we do? So it is of course lambda 0 semi-canonical. Now we take its lambda, it's a one layer map. One layer map should contain everything on this side, and when we're able to add these cells also, because this is half on one side, half on one side, and we will add it, so of course it will be lambda 0 semi-canonical. Because this is roughly half of it, and half of it. So when we take this way, we're still not violating the lambda 0 constants. So all of these cells will be included in the one layer map. Now we take its certified part. Now we have to step up to step one more from the sides, because we need to define the witnesses. Now, what we know is that because of this is a half, so we can surely go to this side and go. So we have an easy certification of the second part of this. Because we just go, we take this and go to this side, and then we have this. Why? Because this is close to a half, and this is very small, and lambda 0 is, actually lambda 3 is much bigger than this. Because here it is the half, epsilon is very small. The requirement of certification here, it should be lambda 3. Our constant is lambda to a bigger constant, lambda 3. So this is how our constants are related. So when we need to take here, this is be close to a half, so adding 2 epsilons will be still much less than lambda 3, so we have this in the certified map. So I mean the other side of this will be easily certified. Now this is a one layer map. So the question was, this was certified because it is part of a canonical word of this relator, and this is because we add this, then still it will be certified. Now, for symmetric reasons, when we take on this side, so we have a different one layer map, but also the both sides of the will be certified. Because because we fixed this word, then the one layer map actually is the path of all canonical in rank k-1 that give us all the possible sides inside this certified one layer map.
Yeah, I missed, where is the relative? I missed.
It is not, no, don't think it about now, because when we define it, the canonical form of angular word, it actually was a covering of the pretzel.
It will be.
It was, we already defined it. Because it was A then it was positive or negative power of B, A, etc. All of this is already of this form. Now, what I'm discussing now, two ways to deal with this series of regions in between. We can compute the canonical form on one side. We can compute the canonical form on the other side. In each case, we know that the result converges to this canonical form because both of these angular relators are already assumed to be in their canonical form in rank K.
You mean that this layer is one layer map for right side and for left
Exactly.
side?
But in the following sense, every time we take a pass, we actually should take the canonical K-1 form of this pass.
I mean that you say that this layer is one layer map for this side and for this side with winners all on one side.
No. Yes, yeah, subject, because when I'm saying it is a one layer map, because I cannot just take a flip, I have to take the canonical form of it. So every time I'm taking the canonical triangle of it. Because it consists only on each side, it consists only on maps or their label must be canonical in rank K-1.
I mean that actually we may have kind of different situation, but I need to draw it, I don't explain it. So when you see, when you have this layer in the form where regions have common paths in a point, like okay, and members of the chart on one side actually have some overlaps. So one layer map for the side, it's in general form with this common parts of measure epsilon. But here we have layer without this small parts of length epsilon. Actually, I mean that we cannot say that this layer is precisely one layer map for the relator.
No, I'm simply just taking the one layer map for this part of the relator, from this point to this point.
Yes, and I say that it's not necessarily precisely one layer map for this part.
I'm just defining it, just it is. I'm not saying that it precisely coincides with this. I'm saying I'm able to draw here the one layer map, and it is equal to this modulo rank K-1. Because in between, I also have maybe regions of rank K-1, just layers of them. I don't know, because I'm using both the canonical form and in each situation, which could be moved by regions of smaller rank.
I mean that even if we have regions of rank K with K equal to 1, then it is precise regions.
Only because the rank 0 is just the void in the free group. But if we take even rank 2, actually we take not the void itself, its canonical form in rank 1, which may move it. Of course, it moves it in the bigger ranks.
Okay.
But what is important is that when we calculate it on both sides, so after all, the canonical form will be identical in both cases, and here there's a solution on one side and a solution on the other side. It means that it must be symmetric throughout.
Okay. Yes.
If it would be some place there is a decision on one side and not on the other, then we must have it on one side. And actually we do not have it. And if it would have a decision on one side, then symmetry would make it equal exactly. Because if we have this canonical map in which coincides in one part, then the rest of the symmetry should be the same.
Yeah, okay.
Therefore, because either it is just the same, which is very good, and just this disappears, or it has this situation of full symmetry in this step of taking the decision about the canonical form when we look what in the short text comparison that should be the same. Otherwise, they could not have two different solutions of taking the canonical form. Or it means that we have the throughout symmetry, which means only the following, that when we look on each of the pretzels that define one canonical form on one side and the other, then it means that the flat should be throughout the whole pretzel. This is the only way that it could be symmetrical both ways, because then we have here, we have a flat around the whole pretzel. If some place there would be interrupt in the sequence of flats, then it should be converged to a certain place. And then they should also here converge to a single place. And this is not the situation now. So it means that this is a most important point. But the only way that we might have a sequence of relations between them, because for both of these pretzels, the sequence of flats goes throughout of them. And then we're able to move it because then the horizontal way just to be moved by power of B in order just to coincide with the other side, modulo things of lesser rank. Then we just take this with this annulus theorem around this, and then after we make the surgery, between them we'll have only regions of smaller rank than K. And then by induction, we have a direct meeting between these regions. For combinatorial reasons, it must be small. And the same argument here works exactly. Therefore, we're able to proceed with our series of derived uncounted diagrams.
But actually, we may have small layer between two regions. I mean that we have this flat around the whole pretzel only when we have this layer bigger than some value, right? If we want to cover the whole pretzel.
It should be an ingredient of it of rank K, but it also may be a lot of them of low ranks. Because our composite flat must have something of rank K, otherwise we would not have here these regions here, they have rank K. So when we go around the pretzel here, some of them must be of rank K, but in between maybe flats of many smaller ranks that connected in this way. And we're able to go around the whole pretzel. This is this. So and then actually is done everything done by induction. But this is most important. But it, by the way, it is a delicate argument here, because the point is we have to compare the one layer map in rank K we compute it on both sides with this map that we see in the derived diagram, they are not actually equal. They are modulo a radius of rank k minus 1 and lower.